secret in this.
There we go.
All right.
Fire away.
Cool. So we're going to chat a little bit about leaky C groups. So, okay, so I don't know how impactful this is. There's a piece of the impact that I'm certain about, and another possible side effect that I'm not sure about. So let me start with an intro, and then we'll talk through briefly through some concepts, and then we'll look at some data. Does that sound okay?
Could you start with the reason that you're looking into this and what, because a customer saw this, what did they see exactly?
Yeah, I don't have the full picture. So it seems to me like there were kind of two. So from what I know, okay, so the way I got involved in this was virtually by accident. I happened to be the on-call engineer when one of the GitLab team members wanted to run an observational test on a production box, and I had already done such a test 2 years ago, so I gave them some context, and we ended up pairing on it for about an hour and learned more about the specifics of the situation. In that case, so that's how I got involved with one aspect of the problem, and then later I found out that there was this separate issue, a separate body of inquiry that was also in progress, and so I kind of tied them together. Okay, so the piece that I know about is Giddily. We do Giddily deploys pretty regularly, and part of the startup for Giddily is setting up C groups, which it will manage, and part of the shutdown is tearing down those C groups. And on some of our boxes, that takes less than a second, and on some boxes, it takes many seconds. And the question was, why? Why is there this big difference, and what can we do about it? And the surprising answer is that historical C groups that we thought that we had destroyed may linger under certain conditions. And so on some of our boxes, we have 0 leaked C groups, and on some of our boxes, we had like almost 100,000 leaked C groups. And certain specific operations have to traverse all of those C groups, whether or not they've been partially destroyed. And that's where Gidlily's startup overhead was coming from. And we'll take a look at that on a live production box in a minute. So Gidly manages 2 kinds of, so we have C groups for folks who may be listening that don't know, because I know everyone here already knows this. C groups is one of the foundational technologies that supports containers, as well as other technologies, and its purpose is to provide a mechanism for controlled throttling of usage of certain resources. So there's a C groups controller. There's a lot of C's in this. Remember, I just got up, so forgive me. So there's a CPU C groups controller and a memory C groups controller. Gidly sets up both of those. There are other C groups controllers that we do not currently use, like the block IO controller, the network IO controller. I'm going to gloss those over. The only 2 we're going to focus on are CPU and memory C groups. And Gidly nodes are leaking both of those. So we know that it's Gidly that's driving most of that leakage. Okay, did that cover? That covered the parts I know. So like Bob mentioned, there's also what appears to be a customer reported concern. It may possibly be related, or it may be completely unrelated. It may be a problem, or it may be a red herring. I'm not sure which. So the customer reported concern, this is in a GitLab issue, which we'll link all of this after the chat. So this is a GitLab issue that's exploring what we've now decided is likely to be a kernel side issue. That this is going to be easier to talk about. So the first body of work I was talking about is only concerned with Gidly having a slow startup time, and we tracked that down to the CPU C group, specifically the CPU C group controller, under a specific action that we'll look at in a minute. But we also know that Gidly is similarly leaking memory C groups, and that may possibly be related to a symptom that this customer observed, which is what I need to fill in some background for. And this is a little hard to do without graphs, but I'll see if we can do it. So kernel manages memory in a few ways. First, the symptom. The symptom that was reported was if you look in any machine's proc meminfo report, there's a bunch of lines of data. Some of these are pretty self-explanatory, and many of them are very much not self-explanatory. One of the ones that is, I think, not easy to understand is just a line called per CPU. And you just go ahead and screen share. This is not interesting yet. Zoom. I can't see my cursor. Wow, I'm apparently having some serious lag. This isn't going to be fun. Wait. I'm sorry. Yeah, I just read cat. I'm sorry. Okay, for those of you that for all of you that can't see my screen, the Zoom widget was covering up my top line, so I couldn't see what I did there. Okay, proc mem info. So this is the line I'm talking about. Usually it's fairly small. This box has about 130 gigabytes, and this is about 900 megabytes, which is not large in terms of percentage of memory. Some folks are concerned about a large value for the per memory metric here. I am not convinced yet that this is a practical problem, but I understand why it's concerning, because a lot of these other numbers don't add up to the total. It's hard to get. What's the right way to talk about this? Let me just leave this at some of the ways that you could add up these metrics to try to make it sum to approximately mem total work well, and some of the other ways that you can try to add them up to make them intuitively add up to mem total really don't work well. And I think we may be looking at a situation where this seems like it might mean something that it doesn't. This is where I need to pause and talk about background for memory allocation in the kernel. So kernel's got two major memory management systems. One of them is called the slab allocator, and its job is, if you've seen, oops, I always do that. If you've heard of slab, these are actually, let me quit this for a second. So this in proc mem info, you've got one line that says, here's how much memory all slab pools are taking, period. You can also look at proc slab info if you're root, and get a very much not human-friendly report that's saying this named slab pool has this many active objects and this many total objects, and this is how many bytes each of those objects is, etc. The columns are listed here. This is really not very human readable, and so one of the usual ways that folks will look at it is spell it correctly. Is a top inspired tool called slab top that will interactively watch changes to the pool and to these pools. So these are effectively this is let me take a step back. If anyone's interested in more about slab, ping me and I'll go into more detail about it. But this is one major kernel subsystem for allocating memory, and it's not the one we're interested in for the per CPU related thing. So I'm just going to stop digging into an unrelated rabbit hole. The other major subsystem is called the page allocator. So when you look at let's say regular top, for example, and it says here's how much memory we're using for the file system cache, for example, or if you look at free, it's maybe easier to look at. So that's how much memory we're using for the file system cache. The file system cache is composed of regular 4 kilobyte pages, And similarly, when a process starts up and wants to allocate memory to use for its stack or its heap, it will allocate pages from the page allocator. So most of the memory on most machines will be managed by the page allocator. And under the hood, the page allocator has two internal subsystems. One of them is the body allocator, which organizes free memory in terms of contiguous chunks, so that when someone requests a large amount of contiguous memory, it can provide it. It can find a memory that's approximately the right size and hand that over to them. The other major piece of the page allocator is the per CPU allocator, and that's what I think that's what's being described by this line. So the per CPU allocator, and I'm going to stop the theory in just a moment and switch to direct observations. The per CPU allocator is it's a subsystem that I have a little bit less familiarity than the body allocator. So I'll tell you what I know, and if you have questions, I may not be able to answer them, but I'll go find out. So it will essentially, in essence, the per CPU page allocator will it will allocate to itself from the regular body allocator a chunk of pages, a contiguous chunk of pages, and slice up those groups of pages, and say CPU 0 gets this piece, CPU 1 gets this piece, CPU 2 gets this piece, and so on. And then the next batch of pages it gets, it will have the same kind of mappings. And so CPU 0 can be assured that it's got this much this set of pages. And I guess the point of this is allocating pages from the per CPU allocator avoids having to acquire a system-wide mutex. And so you don't get in the situation where many processes running concurrently on many CPUs have to compete and be serialized on a global lock. This is why a lot of the memory allocation, a lot of the page level memory allocation really runs through the per CPU allocator rather than the body allocator. Does that make sense so far? So the point here is, I think what this is describing is the total amount of memory that's managed by the per CPU allocator, and not all of that memory is necessarily used or free. It could be in a mixed state. So I've looked at the implementation for how kernel reports this metric, and I'm pretty sure based on that that this is really reflecting that this is really a combination of used and free memory. And so in that sense, I'm not as concerned about a system having a large amount of that memory. The other piece is there is a kernel mechanism for moving the control of those pages between the body allocator and the per CPU allocator. Per CPU allocator can drain its pages back to the body allocator at will, and this appears to be happening regularly on systems, even though this metric doesn't change very quickly at all. So that's kind of another clue that this metric may not necessarily indicate that there's a problem with the system. And I think this was the main symptom that was, as far as I know, this was the main symptom that the customer was reporting on a self-managed GitLab deployment. So I'm missing a lot of pieces for if there were other symptoms, then I definitely would like to know what they are. But for now, I'm thinking that this may not be a practical problem, but I do think it may be a symptom, or rather a side effect, of the memory C group leaking. So in that sense, I want to switch back to focusing on C groups. I'm going to pause here though and see if anyone has questions. Oh, we have a little guest. Hi.
I missed a bit because of that. Sorry.
Okay, so let's see. So I'll screen share again, same box. So this is, there's kind of two ways. So I think you've all seen this before, but each of the C group controllers has a directory mounted underneath sysfs C group. This is the normal way that C groups v1 works. And the CPU C groups are here. You can see that historically these were two separate C group controllers and they've been combined. So now there's a symlink that combines them. So what we're going to do here is, oops. This is, yes, we'll just focus on CPU C groups for now. Every CPU C group is going to have the same structure in terms of its directory, and creating a new directory under this or any of its child directories is how you create a new C group. And similarly, running rmdir on a directory underneath this root C group is the way that you destroy a C group. And in fact, the utility that we use, I'll go ahead and make one now, just so we can play with it. So that's it. We've just created the C group, and you can see that this gets auto-populated with all of the same controls. So this set of virtual files represents the interface for interacting with the C group, and you can see some of them are writable and some of them are read-only. And as you would expect, the read-only ones are providing information, and the writable ones are the actual tunables that you can control. So for example, if we want to add my shell to this C group, we would do it like this as root. Anyway, we don't need to do that, but just as a quick demo. So so when GitLab starts up and creates its set of C groups, it's effectively running. So the makedir utility that we just ran here is a thin wrapper around a syscall that's also, not surprisingly, called makedir, and rmdir works the same way. So I wanted to highlight that these are system calls, because these are the very system call, in particular the rmdir is the system call that that gets used to tear down the C groups. So I'll go ahead and do that now. And we're going to time this. This is not going to be an interesting timing, because most of the actually let me show. What do I want to show? Right, I want to show the leaks. So if we do this, this tells us that there are 621 visible C groups on currently on this box. And if we look in proxy groups, I should show you the whole file so you can see the headers. You can see that for this line for CPU, the hierarchy number we can ignore. The third column, num C groups, this is telling us that there are over 8,000 C groups on this box. So the question is, why can we only see 621 if there are really 8,261 C groups on the box? And the answer is, we've got leaks. And similarly for the memory C groups, this counter is telling us we've got 8,298 C groups. And if we go and look at the reachable ones, we can see there's 629. Most, but not all of these are managed by GitLab. Systemd also creates C groups for its own purposes. We're gonna ignore that aspect. So the question: how
many C groups are too many C groups? Like, do they cost anything?
They don't cost a lot. So in this case, let me. That's a great question. So it depends on the controller. I would say. So as a general rule, C groups are meant to be lightweight. I would worry about a system that expected to have like 100,000 C groups. I think in general, in our environments that we manage in our own infrastructure, it's I would feel a little antsy if we had, like, tens of thousands of C groups. Not but mainly because we've got overhead that comes in the form of CAdvisor trying to scrape metrics for those C groups. CAdvisor is our Prometheus exporter for folks who don't know. And every time we scrape its endpoints, it has to go do a foreground survey of all of the reachable C groups. And in other words, the ones that haven't leaked. And that can become costly. CAdvisor can consume multiple CPUs, and we were in a situation about a year and a half ago, I think, early in the development of the current iteration of GitLab's Gidley C groups, where we were neglecting to destroy C groups reliably, and so every restart would add another batch of, like, 1,000 or 10,000 C groups, and so that added up pretty fast, and that's what kind of made us paranoid about that particular outcome. But yeah, in general, I think having several thousand C groups on a system is not a problem. I'm again mainly thinking of the CPU and memory C groups. For CPU, it really just gives information to the scheduler, and for the memory C groups, each memory C group has its own LRU lists that point to pages that it owns. So there is a little bit of extra overhead if you have a huge number of C groups that can potentially make it more expensive to do page evictions, but kernel deals with that really well. So I think that you can have a healthy system that's got tens of thousands of C groups on it, and that still works under many but not all circumstances. Good question. So what's up with these leaks? We don't yet know for sure how to reproduce them. I have a sketchy theory that I haven't had time to test, so I'll leave that to the end. I want to first focus on sharing solid facts. So we can see that we are leaking based on this. This metric is this metric that's exposed through proc C groups is looking at kernel's counter for how many C groups it has. So the interesting bit that I got from some research is from reading through the kernel code for destroying C groups, is that destroying C groups, which is plugged into that RMDIR syscall. In fact, the starter function for it is called C group RMDIR. It's surprisingly complex, and there's two major phases to it. The first phase, only the first phase is guaranteed to be complete by the time the RMDIR syscall returns, and the second phase runs asynchronously. So these two phases are effectively, the first phase is removing the user interface for that C group. So all of the things that we looked at in our toy C group, those are gone. And some state flags are toggled on the C groups. Each C group has a struct that contains some state metadata, and it's called a CSS. A C group subsystem state is what CSS stands for in this context. So the CSS flags include, and this is where I want to show the BPF trace script I was going to run. This is kind of a summary of those flags, and you'll notice one of them is called dying. Another one is called visible, and as you'll see when we run this script, all of the leaked C groups have the dying flag set and the visible flag unset, and the online flag unset. So that's pretty firm confirmation that they have completed that first phase of teardown and not completed the second phase of teardown. And I think the reason for that, I'm going to kind of spill the beans ahead of time, is that C groups essentially use reference counts. They use reference counting to determine when all references to a C group have expired or disappeared, and at that point they can be cleanly destroyed in that second phase. And these leaked C groups have one reference count left. So I don't know why, and it's a little difficult to trace. the incrementing and decrementing of reference counts, but I am certain, I'm certain that the reference count does not come from a residual task being assigned to the C group. Yeah, so I'm not sure what the reference count comes from. I mentioned that the teardown process is kind of squirrely. It's part of it involves temporarily taking an additional reference as part of the teardown sequence of events, and then releasing that reference once it's reached a certain state. So so I'm not sure if that might be the reference. That's anyway. Let me just go ahead and run this. Let me show you what the toy script is. I've been talking for a long time, so I want to pause and see if anyone has questions, even though we're almost at the end.
I was wondering, like,
Yeah.
what the reference actually mean, but like, what could reference a C group and why?
Yeah. That's a great question. So when we add a process to a C group, that increments the reference counter. When you make a child C group underneath the C group, that increments the reference counter. There are probably other things that also increment and decrement the reference counter, but those are the two that I know of for sure. Another interesting bit. As I think many of you know, there's a C groups v1 and a C groups v2. Those are primarily different. The main motivation for making a C groups v2 was to change the interface that kernel provides to user space in a breaking way. Like C groups v2 puts all of the controllers under a unified hierarchy and imposes some uniform ways of interacting with them, because back in the day with the initial version of C groups, what we now call C groups v1, it was kind of a no holds barred. So every controller kind of made up its own style for interface, and that became difficult to manage. So that's one of the things that changed with C groups v2. Under the hood, almost all of the code is the same. Like these are shared paths, and it's mainly an interface difference. There are some functional differences in the sense that there are a few places in the kernel code where it will call a macro that determines whether or not it's operating in v1 or v2 mode. One of those differences that may not be relevant here, but I'm a little tiny bit suspicious of it, is that for the CPU C group controller, you're allowed. I mentioned how you're allowed to add processes to the C group by writing the PID to this file. You can also add individual threads of a process to C groups, and this means that you can kind of do this unholy act of having some threads of a process in C group A and other threads of a process B in C group B. And this just becomes a nightmare to manage in terms of kind of reasoning about the behavior of the process. So C groups v2 said, we're not going to allow that anymore. Get rid of the per thread assignments. So that is one significant difference. And I don't think it plays a role, because we don't use this interface. We add whole processes to our C groups. But I'm a little bit suspicious that because C groups v1 allows processes to potentially like this is wild speculation. So I said I would keep this to the end. So one possible explanation that I think is probably wrong is that we might have a case where a process is actively spawning a new thread at the same time that we're trying to destroy the C group. Actually, let me just forget what I was saying. I'm pretty sure that's a false lead, and I don't want to waste your time explaining why I think it's a false lead. The other thing that I think is more likely is I mentioned that some of this work gets done asynchronously. Some of the teardown work gets done asynchronously. The mechanism for that is
By whom?
has a frame. Yeah.
So Gitly initiates it, and then kernel needs to finish.
This is all inside the rmdir syscall, so this is all inside kernel.
Okay.
Good. So kernel has very much like Sidekick. Kernel has a mechanism for delegating some pieces of work to be done asynchronously, and in the kernel, this is called work queues. And it works just like you would imagine. There's a pool of worker threads that will consume work items from these work queues and execute them asynchronously. C group RMDIR completes the first phase that we talked about synchronously in the foreground, and this, I think, portions of the second phase do run in work queues. And there's the work queue. There's literally a work queue called cgroup destroy, I think, or remove, something like that. And that work group is, as far as I can tell, that work group is work groups can either be unbound to, or sorry, let me just set the lingo aside. You can either have a system-wide, you can either have a work queue be system-wide, a single work queue system-wide, or you can have separate work queues for each processor on the box, where work items get, so if you're running currently on CPU 3 and you add a work item to the work queue, that work item is guaranteed to execute on CPU 3. And then if your process migrates to another CPU and adds another work item, it will be executed on a different work item on that other CPU, like CPU 3, and then you move to CPU 5 and you enqueue something else, it'll run on CPU 5. This work queue is not guaranteed to be ordered. So that kind of makes me wonder if there's if maybe one of the ways that we're leaking C groups might be that the GitLab process that's running these RMDIRs might potentially migrate between CPUs. When it's enqueued some work items on CPU A and the rest of the work items on CPU B, and these run in unordered fashion. That's a possibility. Take it with several grains of salt, because this is not something I've actually directly observed. It's looking for ways that we could possibly leak, and kernel leaking C groups is not. I mean, the first 10 guesses we have are very likely to be wrong. So yeah. So let me show you what we do know concretely, though. So this is just a tiny shell script that's going to run the BPF trace program that we just looked at. And then oh, I forgot to tell you. So the way that we trigger this bad behavior is so the reason that GitLab spends many seconds during startup trying to create C groups, it's not the creation of the C groups that matters, it's configuring those C groups. So we'll create 1,000 C groups or whatever, and then we'll go configure each of those C groups to say you get so many milliseconds, so many microseconds of CPU time per wall clock time. So we've got to write to these two files to configure that. And writing to each of these two files is what's slow. And the reason it's slow is anytime we write to one of these, so CFS is the completely fair scheduler. It's the CPU scheduler. So anytime we write to these files, kernel will walk the entire hierarchy of C groups, updating their CPU bandwidth according to the new settings that you've set. So even if you're setting this on just one C group that's a child and has no other children itself, kernel will still walk the entire hierarchy, updating all of the C groups, even if they don't require an update. So it's that graph traversal that turns out to be slow, because we're going to do that graph traversal. The number of C groups that we want to configure times 2, because we write to 2 files. And each of those writes, I think currently we're running like 500 C groups per box. So it's 500 times 2 times however many C groups there are system-wide, which currently is about 8,000. And a few days on the worst performing box, it was 80,000. So that's how many times we're gonna effectively visit nodes in the tree. And what we're doing here is creating a throwaway C group, writing to one of those files once.
Why do we need to visit those nodes in the tree when they are invisible? Like, how come we need to visit them?
We don't, but that's just the way kernel does it.
Okay.
I think it also probably isn't strictly necessary for kernel to always start at the root of the C group tree, rather than starting at, say, the C group that you're modifying and any descendants that it has. I'm not sure why it decides to always start at the root. Probably it's assuming that this is a rare event, and it is truly. I mean, people are not changing these tunables all the time, and most boxes don't have 100,000 C groups on them. And even if they do you really need it to be fast to write to this file? So I'm guessing that they did that just so that they don't have to worry about, oops, we missed traversal of part of a hierarchy. But yeah, that's speculation on my part. So yeah, I'll go ahead and run this. It just takes a few seconds to run, and as you can see, the shell script is not doing nothing interesting apart from running the BPF trace script. Okay, so now we'll scroll up and look at the results. So the first bits here are just showing what we already looked at manually. This is the current kernel version. This is from proc C groups, the count, and this is the number of reachable C groups through the find command to look at the directory hierarchy. And we can see there's a big gap there. In fact, we can see that the gap size is, I'm not going to do that math in my head. Oops. Oh, why do I do that? My paste buffer is not happy with me. So 7640. Remember that number as we look down at the flags summary. So first, let's look at this metric. So what we're doing here. Sorry, I should start. Let's go from the top. So we talked about these two. This is showing. So the graph traversal is effectively calling the function that we've instrumented for each node that it visits. And what we're doing here is printing out some metadata about the C group that it's visiting. So this is the ID of the C group. You can think of it as kind of the kernel's equivalent of an inode number. So it's guaranteed to be unique. This is showing us whether or not this particular C group's CSS dying flag is set, and in this case it is. So these are good examples of C groups that have leaked that we would like to not see anymore. And this is the hex representation of the complete set of flags on the CSS, and then there's a separate set of flags on the C group, the C group struct, which in this case is always going to be unset, so you can ignore it.
So that's the dying you were referring to before.
Yes, correct.
First one.
Exactly, that's exactly right. And we're gonna look at that when we get down to here. The other bits I want to highlight are, even though these C groups have been removed from the directory hierarchy, we can still see what their names used to be. So this is the name of that C group. This is the name of its parent C group. And this is exactly what we expect to see. Our naming convention for the Gidley hierarchy is /Gidley at the base, which is very long-lived, /Gidley-PID, which lasts for as long as the Gidley process, and then a certain number of a configured number of child C groups, which we name repos dash and then digits. So this is what we're calling the parent C group from Gidley's perspective, and these are some of its children that have leaked. So we can see that definitely the parent Gidley C group has leaked, and we can see its reference count. This is the reference count we were talking about. Exactly matches its number of dying descendants, and that it has no live descendants. And then we get, I'm just showing the first 10 here, so this is not the complete list of all of the leaked C groups. But we can see that each of the other examples in this kind of head are some of those descendants, some of those 242 leaked descendants, and each of those descendants has a ref count of 1. It has no other, no nested children, but it's got a ref count of 1, which is why it hasn't been destroyed yet. And the parents can't be destroyed until all of its children are destroyed, because each child holds a ref count. Make sense? So the question then becomes, what are you? What are you ref counts? Why are you not 0 yet? Okay, so the rest of this is just kind of showing that there are 3 combinations of flags as we surveyed all 8261 C groups. 7640 of those C groups have this is the decimal representation of the bitmap. So it's got bits set. It's got bit. Sorry, you'll see this down below. So this is kind of the breakdown for the flags on the CSS. Where if the flag is not set, we get a 0, and if the flag is set, we get whatever it's the decimal representation of its bit position is. So that, in other words, there are 621 C groups that do not have the dying flag, and 7640 C groups that do have the dying flag set, and that exactly matches what we were expecting to see from up here, versus the difference between these two. And you can see the same pattern with respect to, are they online? No, the leaked ones are not online, and the live ones are online. And the leaked ones are not visible, and the live ones are visible.
There's got 60 in the root there, and all the rest are these children of.
Exactly. So let's see. So this is not interesting. This is just showing the stack trace for the kernel function that we instrumented with this BPF trace program, and it's of course always the same stack trace. This is a good way to see. Yeah. So you saw in the shell script that what we're doing here is writing to this this CPU.cfs period microseconds file, this control file for the C group. And you can see in the stack trace that the kernel function that we're calling came in through a write syscall. It got picked up by the kernfs file operation write iterator, handed over to the C group file write, which delegated to this function, which is specific to that particular file that we were writing to. So the rest of this is pretty self-explanatory, where this delegates most of the work to setting up the CFS, to computing the CFS bandwidth and setting it on the C group. And then this function is in the graph traversal that we just talked about. Yeah, so that's kind of, the stack trace is kind of a concise summary of what we talked through in the rest of this. Yeah, that's really it. I think the rest of this was just me doing some fact checking, so I can gloss that over.
Yeah, and if I remember correctly from the conversation, this does not happen on kernel 5.4.
Yes,
but anything above that, it does.
We know that it does not occur in 5.4, and it does occur in 5.15, and those are the two kernel series that we're running in production, so we can be confident about that. From just poking around online for other reports of similar symptoms, I found an example of somebody running kernel 5.14 on I think it was on an AWS box. So one of the other interesting bits is all of the GitLab boxes that we're running 5.4 series kernel on are the generic kernel, and all the boxes where we're running a 5.15 series kernel are the GCP fork of the kernel. So there was a little bit of a question in my mind about whether this was a bug in the generic kernel that we inherited, or if it's a bug that was introduced by the GCP fork. If it was a bug that affected the generic kernel, then and then later got fixed in a later release, has GCP backported that bug fix in one of the I mean, we've had a lot of backported patches on the GCP kernel. So I'm hopeful that we may that the 5.15 is not it's not like it's a cutting edge kernel. I think it's likely that we're not the first people to found this, and it's very likely that the kernel community has already figured out the problem and fixed it in a future kernel. And I'm also pretty sure that we don't want to wait for that. So I think probably if we can get a good reproducer, like a nice synthetic way to reproduce this problem that doesn't require good luck or bad luck, as the case may be, then I think it'll be easier to contact GCP and see if they can backport to find what patch fixed it, and contact GCP and find out if they can backport that. So I mentioned earlier in the conference. Sorry, I'll stop screen sharing because there's nothing interesting to see there. I had mentioned earlier in the conversation that I was concerned about this affecting containers running in our Kubernetes cluster. And I have not done a complete audit yet, but in spot checking, I didn't see evidence of this being a serious problem. And I think probably the reason for that is our GCP nodes don't tend to live very long. We don't run them for a year continuously. We do cluster-wide upgrades, periodic, through auto
We
upgrade.
also I don't think we schedule as many processes on them, like as many containers. So we will not be doing as much in the C groups anyway.
Exactly. The thing driving these leaks is destroying C groups, and if the rate of tearing down C groups is low, and the lifespan of the machines is fairly limited, it's not likely to grow to a point where it's going to matter. Also, this only matters under certain operations. Like once the container is running, it's fine. And
we've been running GitLab like this for how long without problems?
Yeah, exactly. In fact, I kind of suspect that this is only kind of catching our attention now because there's an active effort to make GitLab startups be faster. And so something that's taking several seconds on some but not all boxes kind of caught their eye. So yeah, there's a big question in my mind about how much impact this has. But to me, the important bit was this does look like it's a kernel bug, and understanding the scope of the bug and its impact were kind of top of mind from my perspective, and this is where I'm at so far. I'm confident that it's triggered by the C group destruction being only partially completed, and we just saw the evidence for that. And that being the case, I think the rate of we can confidently predict the rate, the upper bound on the rate of leaks is the rate of destroying C groups, and we know that not every time we destroy a C group it's going to fail in this way. So that kind of raises my confidence that this is not going to be a huge impact thing. On the other hand, on long-lived hosts, we can, over time accumulate a lot of leakage, and I don't see I don't see an easy way to clean this up without, like, a reboot obviously would clean this up because it's runtime state. There is a way to kind of force the destruction of C groups, but I think that's impactful to systems, and it's hard to kind of explore alternatives without a reproducer. So that's kind of where we're at right now. At this point, now that we understand the triggering conditions pretty well and the nature of the leak pretty well, I'm trying to get the folks involved to reassess the actual impact. I'm a little bit concerned that
I'm wondering if instead of focusing on this, if getting something HA like for GitLab available is more impactful, because this is not the only thing that is fixed by a reboot.
Yeah, that's true. Yeah. I really kind of, I mean, I'm just going to be frank. I think that this is probably not where the GitLab team should spend their innovation cycles, to borrow your phrase, Bob. I think at this point I want to kind of deprioritize this. Now that we understand the nature of the leak, like intellectually, I like, this is a really interesting problem, but I don't think that this is important enough for us to solve now that we understand some of the dynamics involved. The leak is slow. It only affects certain kernel versions. For self-managed customers, this might be a bigger deal. So in that sense, I'm kind of curious what impact they think they're seeing. It may be that we restart GitLab pretty often on our end, so I kind of suspect that self-managed customers don't hit this very often. Anyway, that's kind of where I'm at right now. I'm trying to find out if there are other side effects that we don't already know about that we need to kind of consider in terms of prioritization. But like, this should not be what drives design changes for how GitLab manages C groups. And I'm a little bit afraid that this may have kind of made people panic a little bit, and I kind of want to dial down the the urgency of it. Does that sort of make sense? I know I'm doing a lot of hand waving here. Let me be more specific. one of the important aspects of like one of the primary motivations for introducing Giddily managed C groups was to ensure that one customer, one project couldn't starve everybody else on the Giddily node for resources. And for that to happen effectively, we decided on per project isolation boundaries to approximate that. And in order to support that, we need to have enough C groups so that when we hash a project into a C group, a bucket, it's unlikely for other concurrently active projects to also hash to that same bucket, because if that happens, then the noisy projects and the victim project that was unlucky enough to land in the same bucket are both going to suffer, instead of just the one project that's being too noisy. So like if we had only 10 C groups, for example, or 100 C groups, most of our Giddily nodes have more than 100 distinct, like their active gRPC calls are kind of spread across more than that many projects. So in that sense, we're guaranteed that there'll be, victims affected. But if we have enough C groups, then it's very unlikely for other victims to get hashed into the same C group bucket, and they'll benefit from that protection. So that's kind of ensuring that we continue to provide the isolation boundaries the original designs we're aiming for is kind of the main thing that I want to make sure that we don't lose sight of in pursuit of chasing a faster startup time that really doesn't seem to be a I don't want to lose the primary benefit of C groups in pursuit of faster startup time, I guess is what I'm saying. And I think that the Giddily team already has a couple of good ideas for amortizing the startup overhead, even on leaky kernels. And I don't think that we should kind of do more than that. I think we should just do those safe changes and not do kind of more intrusive design changes. And that's what I'm angling to try to get.
Thank you. Now I know what you were doing.
Yeah, it's kind of a little unusual. I'm doing this work to understand the nature of the problem, and now I'm trying to use what I've learned to de-escalate work that I think we can probably afford to not do. It's not usually the direction we go, but in this case, that's kind of I think that's what's best. All right, so I just blathered a lot. Anybody? Yeah, sorry, go ahead, Bob.
I need to drop off. I can keep the recording running. I don't know if somebody else wants to share anything or has anything to add. Otherwise, we'll see each other next time. Bye-bye.
Thank you, Mark. Thank you, Bob.